I want to welcome everyone to our monthly EPIC seminar. Today we are very fortunate to have George Crabtree. He's a senior scientist, distinguished fellow, and associate division director in the material science division at Argonne. George has won numerous awards for his research. He's won the U of C Award for Distinguished Performance at Argonne twice. He's a U.S. Department of Energy's Award for Outstanding Scientific Accomplishment in Solid-State Physics. Not once, not twice, not 3 times, 4 times. He has an R&D 100 award for his pioneering development of magnetic flux imaging systems. I certainly have no idea what that is.
It's really important.
Okay, but it's very important. And won an award that I can't announce, the Onus Prize in 2003 for his work on the physics of vortices in high temperature superconductors. He has many other accomplishments and affiliations, founding editor of the scientific journal Physica C, charter member of ISI's highly cited Researchers in Physics, member of the U.S. National Academies of Sciences, and has done a lot of important work at the department involving the Department of Energy, and testified in front of Congress several times, which probably should get an award for that as well. So anyways, we've been very anxiously awaiting your talk for several months and are excited to hear what you have to say.
Great. So what a pleasure to be here, and thank you, Michael, and everyone else who made this day possible. I arrived here at 9:30 this morning, and I have not stopped since then, talking with people, really lively conversations, so I'm thrilled to make the connection, and I hope that we can expand on the foundation that we're building, we're laying today. So what a thrill to be here. Learning about what you guys are doing, what EPIC is doing, and to think about the possibilities for perhaps working together going forward and accomplishing some common goals. I think this would be really, really wonderful. I got to tell you, I'm a guy that likes to be interrupted, so I'm going to tell you some stuff, but if a very important question or comment comes into your mind, please do interrupt me. I may not be looking, I may not see hands raised, and so don't be afraid to just shout it out. It's way better to have a conversation, I think, than it is to listen to a monologue. So let me say that at the beginning. So I would like to talk about, I don't know which way to point, but the impact of next generation electricity storage on the grid. It's a huge topic. There's no way it can be covered in one lecture, even 45 minutes or so. So I'll hit the high points, and I would consider the things I'm going to tell you to be the basis for discussions that we may have today or later on. I hope I can provoke you a little bit. I'm going to tell you some things that you may not have heard before, and maybe nobody's thought of at a deep level until now, and I hope this starts some conversations. So I want to talk about transportation and the electricity grid. Those are the 2 frontiers that are waiting to happen for energy storage. A little bit about central and distributed storage. So historically it's been central, what's coming is distributed, and how do you think about this? Very important point, I think the grid is changing, so the grid of the future will have 3 things in it. It'll have storage, which it doesn't have now. It'll be smart at a level that it is not smart now, so we're starting to get smart, but we got to get a lot smarter. And it will have this distributed architecture, which is really different and takes a much longer time for the transition to take place, but it will have that. And then I want to talk a little bit, I can't resist being a little bit technical. Lithium ion, that's today's battery technology, which is absolutely phenomenal and has dramatically changed personal electronics. But then, is it good enough for transportation in the grid? I'm going to say no, it's not. So I could be wrong, but I don't believe it is. You need the next generation, which I've listed here as beyond lithium ion. So I want to at least kind of make that, pose that question. So if you want to know more, this is a review article that was just published last week an MRS bulletin, which talks about both lithium-ion and beyond lithium-ion and the challenges of the grid and transportation. So here's a very long URL. You can download it, or you can just Google MRS bulletin, which is where it appeared. We also have a website. The URL is there. It's pretty lively. It changes a lot. We keep it up to date. I like to browse it, actually, the way I browse the New York Times. So you're not me, but I can look at this website for an hour and not be bored. So, it's something to keep in mind. So let's start with the intellectual content. Go back to 1991. That's when the lithium-ion battery was commercialized by Sony. It made possible all the personal electronics that you see in that picture. In particular, the cell phone, which I think is the thing which had the most impact on people's lives. It changed for me the way I communicate with people. So I don't send emails. I don't even do this. I do this. I'm texting all the time. And that has dramatically enabled me to get a lot more done. I think we all feel that way. It also changed the way that we deal with information. If I want to know something, I tap it into my laptop or my cell phone, I get the answer right away. So it changed permanently the way society works in terms of personal interaction and interaction with information. So a tremendous thing. There's two more revolutions that could happen. One is the car. And if you had, for example, a 20K electric car that went 300 miles, here's some of the things that you could do. You would probably displace a lot of gasoline cars. You would replace foreign oil with domestic electricity, probably a good thing. You would reduce both energy use and carbon emissions, depends a little bit on where the electricity comes from, but it has that potential. So this could be a transformative change in society. The second thing is grid-scale electricity storage. So it's a real game changer. If you think at the highest level, since the grid was the advent of the grid more than 100 years ago, we've had to generate energy at the same rate that we use it. And we've learned how to do that pretty well. So we kind of don't notice it. But it's a huge constraint. It means that you have to build the grid, the infrastructure for the peak. The peak is about twice the average, which means you're building twice the infrastructure that you need to build. It also, storage on the grid would enhance reliability. Think of Superstorm Sandy. Flexibility and resilience, so all of these things would get better. It would enable renewables to be deployed at a wide scale. They're inherently variable, their generation, unlike the demand variation, which is pretty predictable. That of renewable wind and solar is not. So you need a way to smooth out the fluctuations and make them dispatchable. So lots of things that grid-scale electricity storage could do. If you think in purely energy terms, and I want to make the connection energies to dollars, but I won't make it explicitly, let's just stick with energy. The two biggest, these are all the energy uses in 2013. So the two biggest ones are the colored ones, the electricity grid, 39% is huge. That fraction of our energy comes through electrons. The other big one is transportation, 28%, that's the gasoline in your gas tanks. This really accounts together, that's about 2/3 of the energy we use in the United States. Compare that with personal electronics, and that's where most of lithium-ion batteries are. That's less than 2% of the energy that we use. So in energy terms, if you captured half of the transportation and grid market, it would be more than 10 times bigger than the uses for which we now use lithium-ion batteries. So it's a huge business opportunity as well as an energy opportunity. And these are the things we were talking about in the last couple of view graphs. So it really is much bigger than where we are now. Let's think about these two things. I want to talk mostly about the grid, but first let's compare it to transportation because they're really, really very different. So when it comes to transportation, we've had gasoline cars for a long time. They provide some transportation services, And the challenge for electric cars is to provide those same services, but in an enhanced way. So cheaper, less emissions, and various things. So it means that the primary challenge, there are 4 primary challenges. Here's the first one. You want to be able to go hundreds of miles instead of tens of miles, as you can now with a Nissan or a Volt. You want to have fast charging. Instead of 10 hours to charge, you'd like to charge in minutes, so minutes instead of hours. It has to be inexpensive. I've taken the number 20K, but you could take another number. Instead of 80K, which is the price of a Tesla, which does all these things, but it's just too expensive. And very importantly, it has to be safe, both in routine operations and in case there's a crash. And you could imagine a crash where the battery is penetrated and it's raining outside and reactions take place and fires and so on. So we really have to solve that problem. There's some secondary challenges. The main one is charging infrastructure. We really don't have it. Maybe it's not so hard to get that. Electricity is almost everywhere in our lives, so you could imagine just hooking up some charging stations and solving that problem. And the takeaway message here is that you want to provide the same services that fossil fuel does, but you want to provide them better. There has to be a reason why you go with electricity instead of fossil fuels. Very different from the electricity grid challenges. There you want to provide a new set of services, so you're breaking new ground. You actually want to do things much better than we do now. So, for example, you want to firm the fluctuations of solar and wind. So on a second-by-second basis, if a cloud comes by or the wind stops blowing, you want to smooth those fluctuations out. You want to time shift excess renewables. So the wind blows harder at night typically than it does during the day. The sun, of course, goes down. And the biggest peak time, peak demand, is right after sunset. So that's not when wind and solar are producing for you. So you want a time shift. You want to replace peaker plants. So plants that run a few hours a day only are usually very dirty. They're expensive. They're not efficient. They're the old technology that you don't want to run very often. You want to replace that with stored electricity that you got from the cheaper baseload and cleaner baseload. You might have frequency and voltage regulation for digital quality power. That means you need a high power battery that you switch very often between adding to the grid or storing from the grid. Very different from the other applications. And very importantly for the grid of the future, you want to integrate storage with smart and with distributed energy resources to build better services for the customers. So those are dramatic challenges. They're diverse. They're different from transportation in that there are many places where you need storage to provide service you don't have now. There's lots of secondary challenges too. So one of them is the regulatory environment. So it was never made for storage. Storage doesn't fit into it. The regulators are risk averse. They don't want to let the utilities do anything that's going to raise the cost or that's going to fail or that's going to sort of challenge reliability. So they don't like experiments. And if we're going to understand how to use storage, we have to do a lot of experiments. Some of those are going to fail. We just have to do that. And the second challenge is business plans. So utilities really don't know how to embrace this grid of the future that has 3 things in it: storage, smart, and distributed architectures. They have no idea how to play in that game. So they're learning that, but it's going to be a long process. So those secondary challenges, unlike transportation, are much more complex and difficult. In the case of transportation, the market decides, right? If this is a better deal, I'm going to go for it. So this is the takeaway message: dramatically different architecture, functionality, and services. New horizons for innovation. It's richer and riper than transportation. So let's get to the grid. Here's the history of the percentages. All it says there on the left, but that's a percentage of primary power that goes into the grid. And you see it's done nothing but go up. It's around that 40% number. It's going to go up even more if we get to electric cars. That'll bring it to new heights. This is the way the grid works. So you have generation on this side, typically with heat. So by burning coal or gas or the heat of fission, you make heat. Sorry for that T falling off. You turn that into mechanical motion with some kind of an engine. You stick a generator on the end of a rotary shaft to produce electricity. It goes into the power grid, gets used for all of these things. There's lots more ways to produce electricity that I've shown here. That's the traditional way. You could get the heat from the sun. You don't have to get it from combustion. You don't even need the heat at all, so hydro and wind give you motion directly from natural sources. You don't even need motion from solar PV. You can get electricity directly from the sun. You can also get electricity from fuel cells, so you need some energy source there, some chemical fuel, but very clean and very efficient. And if you look at where the problems are, they're pretty much here. So the traditional generation, 35% of the energy goes into electrons. It produces a lot of CO2 emissions, and this is the energy that's lost. But from this point on, this is a really sustainable, clean system. So electricity has a lot going for it. You think of it, the electron is produced, it goes through the wires, it does its work, it loses its voltage, it goes back. You never know that the electron has been there. So there's no chemical change at the point of use. So in that sense, it's really an attractive way to deliver energy. It's interesting to think that on the generation side, it's usually central. On the use side, it's usually distributed. And I want to use that division in the next few slides to think about where we could go with storage. So here's what's happening with wind and solar. Starting to take off around around the turn of the century or so. Wind has done much better than solar. Although solar is growing, the prices are falling, and we can expect that to grow at a really high rate. If you just look at the numbers, so this is the capacity, 60 gigawatts on that scale, another 10 here or so, call it 70. But there's a capacity factor of somewhere between 15 and 30% for solar and wind. So you got to lower that. We're getting, it says there 3.8, it's really closer to 4.8 now. If you look at the extrapolated growth rates, if you kept a 15% growth rate, we would be 40% wind and solar by 2030. So we're, in a sense, on track. This could be done. It's very variable. So this is the output of a wind farm, typical wind farm. They all look. Yeah.
I want to interrupt. If you
Yes.
go back, if you go back
Sure.
to like 15% growth, but we think that the costs that they impose on the system go up, that they account for a larger share
True.
of the system.
So at 5%, if that was really 5% and not 3.8, you kind of don't notice it. It disappears into the environment. If it's 40%, you have to worry about all those fluctuations and where is it installed and so on. Good point. Right. So what do you do about those fluctuations? Well, what you do right now is you build a gas plant right next to the wind farm. And on the days or when the wind doesn't blow, remarkably, you can see it here. The wind output, here's a day when there was no wind output all day, and here's another day. So on those days, you need something, especially if it's 40% of your electricity. So you build a gas plant right next to it. You're building twice the infrastructure that you really need. The logic here, be logical, you would ask, why did I build a wind farm at all? I'll just build a gas plant. It's not the outcome you want. So the question is, can you back up the wind farm, not with a gas plant, but with a battery? Right now, the cost of producing electricity from a battery and from a gas plant differs by about a factor of 5. So you have to get the cost down by about a factor of 5 in order for this to be the winner.
And that's with today's natural gas prices, or?
Yeah, and they're varying. So, but it is with today's natural gas prices.
And in Asia, which has whatever it is, 3 or 4 times higher natural gas prices, it's 20.
Then it starts to look a little more attractive. Absolutely. Yeah. It's not. It's of course the cost of building the plant is factored in here too.
Yeah. So it's not.
Was there another? Yeah.
What ratio to demand do you have to build a battery backup? Gas plant, I could see 1-to-1 to your peak demand on a battery. How much do you have to account for so you don't drain the battery?
Yeah, good question, and you'll find various numbers in the literature. And I think all of the practice we have, the experience we have, is with 5% penetration. At 20 or 30%, it would be a different number. And I'm not sure we actually know that. Everybody quotes Denmark, but Denmark is embedded in Europe, and they have a wonderful sink for all their excess electricity. So I don't think that's a real number. It's a good question. Yeah.
I expect at some point you get to lifetime with the batteries, but gas plants typically last 30 to 50 years as well, where batteries stay are, what, 5 years?
10 to 50, depends on the battery. A flow battery might be 20. A lithium-ion battery is probably 10 or less. Yeah.
Wish I could get 10 on my personal computer.
But we actually don't know. So the car companies are giving you a guarantee on the battery. I think they really don't know what the real lifetime is. We need to have some more experience, but good point. So there are other ways, apart from renewables, that you can use storage on the grid. So this is the UK electricity demand. Everybody knows this curve. This is the peak here. It's about 6 o'clock at night. And the way you deal with that is base load, coal or nuclear, for example, dispatchable power, which might be natural gas, and then it's pretty clean and pretty inexpensive, so that's good. The peak power, on the other hand, is usually dirty, inefficient, expensive generation. It's typically old. And wouldn't it be better to charge a battery when you've got excess electricity that is demand is low? Maybe you do it from base load, which you bring up a little bit in this storage scenario, and get rid of the peak power plants. And you have to point out, since you guys are economists, that the peak power plants are expensive. That's low-hanging fruit. It's not so hard to meet the bar to replace those peak power plants with storage, though it's not being done. But that's easier than displacing this dispatchable power, this green stuff. So that's what you'd like to do. The tipping point, and back to the cost of batteries has to be less than the cost of the peaker plant. Yeah.
So that 5 times greater number, is that for the expensive peaker plants?
No, that's more for, you'd be down here. It's easier for the peaker plant.
So what is the number, do you think?
I don't know what it is. We need to, and it probably varies depending on where you are. I would actually like to find that number, because I would like to start making the argument that let's do that, and maybe we can do it now. It's possible in some areas that makes sense. Yeah.
Isn't it a little harder than that, because you've already got those peaker power plants, installed, and you only run them, an hour a day or maybe tens of hours per year, so they don't have a lot of wear and tear. So not only do you need to be cheaper than them on sort of like the cost of the fuel, but you need to be sort of even cheaper than, or you need to be cheaper than the cost of fuel, not just the fuel plus the capital cost, right?
So absolutely, you don't have to buy the peaker plant typically because it's an old one that you already bought and paid off. So that's something that you have to factor in. Operationally, I think the cost is high, but you have to do the whole calculation. Absolutely. Yeah. So let's talk a little bit about distributed. So the stuff I'm going to say applies equally to the electricity grid, to the internet, or to highways. Same kind of thinking counts. We all know what centralized is, and this is all roads lead to Rome. Or in the case of power plants, this is, well, first. Then there's decentralized, so you might have several power plants that are connected by, let's say, high voltage lines so they can share power. Or you might have a distributed network that could look something like this. And if you look carefully at where the dots are on these 3 diagrams, in all 3 diagrams, the dots are in exactly the same places. So it's a question of how you draw the nodal, connect the lines between the nodes. So you might think of this kind of a fully distributed system. And if you go back until sort of the late 1960s, it was all central power plants. They were expensive and pretty much unique. Every one was different from every other one. There was an economy of scale. Let's make it big, then we can supply the power cheap. They were typically unreliable. It was not unusual for the power plant to fail. And then, of course, everything that it served was without electricity. At the same time, the grid was rather inexpensive. It was reliable, so most outages were due to the central plants and not to the grid. That began to change in, say, the 1970s to the 2000s. So we learned how to make power plants pretty well. They became less expensive. They became much more reliable. We began to be aware of the fossil, the nuclear, environmental stigma, and of course hydro's fine. By contrast, the grid became expensive. There was a regulatory challenge, so it can be as much as 10 years to get a new high voltage line approved, especially it has to go across more than one state. And it became unreliable, so most of the outages were due to the grid and not to the power plants. More recently, 2000s till now, we started to get wind and solar, which is inherently distributed, especially rooftop solar. These things are inexpensive. They generally last a long time. They're mass produced, so the value here is not an economy of scale. It's that you can produce them cheaply and sell them all over the place, identical plants. The electricity grid problems got worse. It's aging, outmoded, a security target, starting to become smart, and that's something that we should welcome. But because of this trend, the fact that, we favored centralized plants early, we now favor distributed plants. It makes sense to start thinking in distributed terms. So that's the bottom line here in the yellow box. So let's think for a minute about the electricity grid. It started out as one-way power flow. If you have distributed rooftop solar and you're producing excess electricity, it has to go somewhere, so you need two-way power flow. You need intelligence to control that two-way power flow, and I think we're just breaking the ground here, scratching the surface. If you add storage, you add, in a sense, a third dimension. So you now have a place where you can put that excess power and use it later, bring it back. This added an intelligence infrastructure to the power infrastructure. This adds another dimension. It's a storage infrastructure. And the question is, of course, where do you want to put it? Do you want to put it at the central plant, or do you want to put it at the end point of use? So, already said that.
Can you go back a slide?
Yeah, sure.
What is the intelligence you're talking about here? Like, what are the facts that grid operators need, or power plants need, or consumers need? So prices are the ones that we economists always think about. But are there other? What else goes into intelligence?
Yeah. So right now we have smart meters. That's mainly to make it easy for the utility to charge you and know what your use pattern is, and if they want to say, can you use a little bit less electricity now because demand is high? That's kind of the level of smartness that we have. You'd like to have smartness at a much higher level. So you'd like to, on the distribution grid, you have excess solar from the panel on your roof. What do you do with it? Where does it go? Does everybody in the neighborhood have excess? And if so, that's a lot of excess. So what happens to it? I think we don't make those kinds of decisions now. And many of the outages that, even up to 2012, have been due to the fact that we weren't able to decide quickly enough to change the electricity sort of route. So I'd throw a switch and won't go here anymore, it'll go there.
So the intelligence, for the most part, that we don't have yet is better data on quantities.
It's not only data, it's decision making in real time. So instead of an engineer somewhere throwing a switch, it happens automatically. It doesn't have to think, it just happens quickly. And you can model it depends on the size of the grid you want to model. So you could model the local grid in, I don't know, let's say Naperville, or you could model all of Chicago or all of Illinois or all of the Midwest. The bigger the box, the more value you could potentially get out of it. I think we haven't gotten there yet. I mean, we're at the low level of smart meters, that's all. So let's think a little bit more about that. And this is the grid of the future. So distributed energy, energy storage, and smart grid. And I'm going to use the word microgrids, but quite often you just say distributed architectures. So here's an example. Here's a little microgrid. It might be for a neighborhood of homes, but you could imagine other uses, and we'll get to that in a minute. It's connected to the main grid, so it's not independent. We're not islanding here. But within that microgrid, I'm going to suggest anyway that there ought to be two features that are critical, that have to be there. There has to be local generation, so rooftop solar would satisfy that, and there has to be local storage. So it can act somewhat independently of the main grid. Of course, there will be uses. If it's residential, you might want to plug your car into it, you would want to have some storage. Your use pattern in a house, so you're there all night sleeping. Some people are gone during the day to work. If there's no kids, maybe everybody's gone. And that use pattern is very different, for example, from a commercial building, where full of people all day and there's nobody there at night. So you can imagine just those two examples, that there are very different use cases that you would want to design the microgrid and the storage capacity it has, and the generation capacity it has for the end case use. So these are some of the things that you should have. The advantage of short delivery, that's what, the fourth bullet there. So I'm producing within the microgrid, I'm using within the microgrid, so I don't have to send it long distances, yeah.
If we build out these microgrids all over the country and pick a number, 50, 70% of the electricity that we're using is coming off of these microgrids, but we're continuing to have the full grid.
Right.
How do you charge for the grid, and who ends up paying for a grid to be there when most people aren't using it 70, 80, 90% of the time?
Great question, and there's no answer to it. So I think this is the question that the utilities are facing.
There's a very painful answer.
Say?
You have a two-part tariff. You could charge people for the fixed costs for getting connected to the grid. It would be very regressive. And then you could charge them a different price for each amount they use, each kilowatt hour they use. That'd be the way, that'd be the simple, is that right, Mr. IO Economist?
Two-part tariffs, yeah.
Yeah, two-part tariff.
But that cost ends up being the same though, because when they just do on a per kilowatt hour basis, they raise the charge because those fixed costs are the same.
So currently, the way it's done is the fixed cost is buried in the per kilowatt hour charge.
Yeah.
And that's what's causing all this pain for related to the idea of switching to a new system. So, but I think that's because they want, I don't know what, these guys probably know better than I do, but I think the history of that is a way to make it less regressive, is that right? Yeah. So, a very painful thing, and very regressive would be to go to a full two-part tariff, and if you want to be connected to the grid, you have to pay whatever it is a month, and then you can buy electricity at its true marginal cost after that. Right now, we pay a higher price.
So I think one of the things that some utilities...
It's a real dilemma. There's electrical companies that are denying people the right, especially in Hawaii, where they just had a huge law case, of selling their excess electricity back to the grid because the electric companies can't make enough money to support the grid for everybody. And the more people that go off, the worse the problem is.
Well, that had to do with pricing as well. The price for solar in Hawaii is way inflated over the wholesale price, which is the actual value of the electricity delivered. I mean, even in Illinois right now, the wholesale price of electricity is about 4 cents per kilowatt hour, but we have net metering that's 12 cents a kilowatt hour. So there's a question of why we should subsidize someone who puts solar cells on the roof and gets 3 times the actual value price of the electricity generated.
So these are questions that, in my view, haven't been answered yet, but I agree they're and they change depending on how many people have solar. So if only a few have, well, who cares? If it's 50%, then you really have to think about that. And this is what I was saying earlier. I don't think the utilities and the regulators have a business plan in mind that accommodates this. So some utilities, I'm sure, will use this as an opportunity to resist solar panels. I'll make it so expensive that you will never do it. And that, of course, is not the goal. You want to provide services better than what we have now. So a way that achieves that and still is fair to all consumers and utilities alike, I think, my sense is we don't have it. You guys may have other opinions, and that's great. So this offers, I used the word personalized energy here in the last bullet. It offers the chance, a little bit like your cell phone, which you personalize for you, or maybe your house or your neighborhood, to personalize the electricity service that you get so it fills your needs. And this is a concept we haven't really explored. I have a feeling because consumers are this way, and cell phones certainly back this up, that the more convenience, the better. We're willing to pay for that convenience. And it's a question of how much is it really worth. So I'll have things set up for my particular lifestyle needs, and yours are different. Can't do that on the grid at the moment, or at least not very well. And this is actually what I was saying earlier. So think of the kinds of services. So a house, a neighborhood of houses, an office building, shopping center, a factory, a campus, a military base. They all have different use profiles. They would all need microgrids with a different level of generation and storage. And they would have different use patterns. So one size does not fit all. One could really customize. You could imagine a DC microgrid. So almost everything, I'm looking around the room here, and I'm seeing lights, that could be DC. I'm seeing a projector, that could be DC. A lot of the computers are DC. So a lot of the uses we have are DC. And in fact, the first thing you do when you take AC out of the wall is convert it to DC, 5 volts, and then I'll let it do what it wants to do. So you could imagine that some microgrids, I left a very important one out, solar panels are DC. So you can imagine that some microgrids would be able to do all of this, never going to AC. Short delivery distance within the microgrid, so you don't have to send the electricity very far. People have started to think about this, but not really, I think, at a deep level, but it is a possibility. And then you could imagine a network of interacting microgrids. So that's a microgrid, that's a microgrid, that's a microgrid. Along comes Hurricane Sandy, and it goes through here, and all the microgrids in its path are lost without power, but they share with their neighbors. So indeed, it has the potential to be much more resilient and operate in very, very different ways. So we've, in a sense, already talked about this, but here's a picture. I've got the grid, I've got solar panels, with the way it works right now, net metering. If I have excess electricity, I sell it back to, here it looks like it just goes into the grid. Well, it has to go somewhere. That means the utility is fully involved, whether I'm selling electricity to the utility or using their electricity. They're involved in every part of the transaction. If I put a home battery in my garage, then suddenly I'm storing the excess electricity that I have. I never put it back on the grid. It's a different operational plan. And this threatens the utility business plan. This is what we were saying earlier. I don't think there's an answer to this yet. We need to find one. So we have to figure that out.
Can you go back to that point?
Sure.
It seems like by the time that batteries are cheap enough to sort of arbitrage that difference between the sort of the low demand and the high demand state, it seems like there would be some kind of economy of scale where a utility would rather use those batteries, and it would make more sense to do it at a larger scale than for somebody to do that inside their home. So why do we have an expectation that this thing will first appear inside people's houses as opposed to...
Partly because of Elon Musk, who pushes hard on this idea, and I really give him a lot of credit. I think he's starting the conversation. I also agree with you, and everybody who's done the analysis, it doesn't really make sense at this stage. Batteries have to be a lot cheaper. And I saw in Bloomberg after Musk talked about the home battery, it was last spring. A simple back-of-the-envelope analysis. You can get 5 times more electricity out of a diesel generator than you can out of a Powerwall. So it's really still too expensive. So you're right. And why wouldn't you have a neighborhood of homes and one community battery that did this, or a commercial building battery that was way bigger than these things? Yeah.
They're already showing up in manufacturing plants. Johnson Controls will drop off a truck trailer. It's full of batteries. It sits out behind the plant, and they're doing exactly this, just on a larger scale.
It seems like the natural evolution would preclude this, right? We talked about Hawaii. The homes would probably be installing these kind of units that may become more broadly adopted at the home level. So as that capability gets better and better and better, why would somebody suddenly, as you get maybe 80% of the residents or businesses are using their own local energy, why would they suddenly say, oh, you guys have all of the batteries and we'll go back to the centralized plan?
Yeah, I guess I'm sort of asking, I'm assuming that you're not putting it in until it's actually worth paying for. I'm sort of postulating that. I don't sort of know the number,
Yeah.
but I'm postulating that it would be worth paying for on a large scale before it would be worth paying for on a small scale.
So, although that may be true, one thing you lose from that is customization. If it's in my house, I can make it work for me. If it's in my neighborhood, I have to agree with my neighbors. If it's more centralized, then I kind of have to take what the utility offers.
Could you talk a little bit more about customization? So what exactly, constitutes differences in people's preferences about, say, electricity?
Well, so I leave for work at a certain time. You don't. I come home at a certain, maybe I come home for lunch, maybe I don't. Maybe my kids are in the house and, they have a schedule that requires them to be at home at certain times. And I'm using electricity then. So I want to have the services available when I'm there, and when I'm not there, I don't care.
So I think you currently have that though, right?
Sorry?
You're currently able to sort of, not.
I can turn it on and off.
During the morning.
Yeah, but maybe I can get it a lot cheaper if I only wanted it at night, or if I only wanted it during the day.
So-
If I have one rate, I'm stuck with that rate.
But that's kind of a statement about the way prices are set, right? I mean, you might be able to find a utility somewhere that will actually give you a time of use price, and you pay very little to use it overnight and more to use it at 6 p.m.
Yeah, but if it's time of use and I want it during the day when it's really expensive, maybe I want to buy it at night, store it, and use it during the day. One has to do the case. I don't think we're there yet. I agree, but you can imagine getting there. Just like, let's say in the year 2001, you couldn't imagine the cell phone's going to be so useful to you that you would pay hundreds of dollars for it. And I'm kind of wondering, why do I do that? But I do. And I think a similar case would apply here. So it's partly behavior and partly how you think. So, this is a great subject. Okay, let me switch a little bit. What kind of battery could deliver all of these things? And I want to concentrate on lithium-ion batteries, which were conceived in the early 70s, so 1971 roughly. And what the idea in 1970 was, I'll have a pure lithium metal anode and some kind of an intercalation cathode. And in fact, this is an early version of such a battery. Titanium disulfide was the cathode. It had, this was 1977, commercialized, had to be taken off the market because there were dendrite problems. You couldn't really develop a pure lithium metal anode, and in fact, this battery had an alloy anode, but it didn't make it. 20 years later, that's what this arrow is. 20 years later, 1991, lithium-ion batteries were commercialized by Sony because they wanted them for personal electronics. The battery that came out in 91 didn't look anything like the thing that was conceived in 71. It had a graphite anode, not a lithium metal anode for safety reasons. That's the best they could do. And when it came out, it was about twice as good in energy density, so that's on this side, in energy density than the best available at that time. That was a huge jump. It made a very big difference in personal electronics. And the energy density grew by another factor of 3 since 91 due to materials research and so on. So we're looking at about a factor of 6 better than what it was in 91. And the cost came down, so a factor of 10, this is the cost curve, came down by about a factor of 10. That's what made personal electronics happen, this curve. You can now ask, there's 2012. So let's look at the future. So if we want to do this for transportation and the electricity grid, what do we need? And you could imagine that lithium ion is going to continue to get better for a certain, it has a certain headroom it can achieve. It will eventually hit a limit. Some people say that limit is 50% better than it is now, and we really don't know where that limit will be until we hit it. But you could put your faith in lithium ion getting better, or you could put your faith in the next generation of batteries beyond lithium ion, which presumably, when they come out, will have a discontinuous jump here in performance, and they'll continue to get better just as lithium ion did. So many people, I'm one of them, feel that lithium-ion will not get to the point where it can enable electric cars to displace gasoline cars and for the grid, that we need the next generation.
And why, is that a physical reason or a material science reason?
Yeah, so it's limited by the fact there's only one charge on lithium, by the fact that cathodes, so they're now cobalt oxide, have a limited capacity, and you can make it better by various tricks, which is sort of what this curve is, all the tricks that have been done to the cathode. And you can make the voltage a little higher. It's about 4 volts now, 4.2 volts. You might make it 4.5 volts. You might make it 5. But you're not going to make it, you will not make it a factor of 2 better. So that's a physical limitation. And, you know, like Moore's law, you keep finding ways to extend that curve, and maybe we'll be innovative enough to get to the point that we need. It doesn't look likely to me and to many others. So a little bit of advertising. So here's Joint Center for Energy Storage Research, that's J. Caesar. What's our vision? Our vision is to transform transportation and the electricity grid with low cost, high performance storage. We want to bring out prototypes, one for the car, one for the grid, that perform 5 times better than lithium-ion batteries in 2012. That's when we started, so not now, but in 2012. And 1/5 the cost. And why do we have this transformative goal? It's because we want to make not just a competitive electric car or a competitive battery for the grid, we want to have a transformative one. And if you want to be transformative, these goals would certainly achieve that. Maybe something less than a factor of 5 would also achieve, but we're shooting high. We want to do this by leaving 3 legacies. We want to understand the fundamental science of materials and phenomena of energy storage at atomic and molecular levels. So we've had 15 years of nanoscience. Has not been applied to energy storage to the extent that it could. We want to have 2 prototypes, one for the car, one for the grid, that will look totally different. Whoops, excuse me. Because the uses are different, but they might be based on the same set of fundamental knowledge that we get in the first legacy. And we want to have a new paradigm, and this may be the most important thing, for battery R&D that operates very differently than today's paradigm. It would combine 4 things in one organization, and the 4 things are discovery science, battery design, research prototyping, and manufacturing collaboration, all talking to each other. So today's paradigm, those functions are done by 4 entirely different entities. The discovery may happen at a university. The battery design requires more than most university groups can do, so that would be done by somebody else. The prototyping might be done by a 3rd group, and a manufacturer would certainly bring it to market. So we want to talk across that spectrum. So if the manufacturer says, don't give me any battery based on the following materials, it's too corrosive, way back at the discovery science phase, we just won't bother with those materials. So we should be able to accelerate the progress significantly. This is, I think, critical and a little bit technical, but not terribly. I want to compare lithium-ion with beyond lithium-ion, which eventually will appear here. So I plotted here the systems, which means the concept for the battery. There's one concept for lithium-ion. It's an intercalation anode and a intercalation cathode, graphite and some metal oxide. Here's the materials. There may be 5 or 6, maybe 7 materials that are under consideration for lithium-ion batteries. By contrast, the beyond lithium-ion space is way bigger. This is mostly known because they've been commercial for 25 years. You can make incremental advances, but not transformational ones, because you saw the 5% per year is about what you can get out. The beyond lithium-ion is different. It's mostly unknown because we've had lithium-ion batteries have served our needs. We've no need to look at these. And you can get transformational advances. You can get the factors of 5 from beyond lithium-ion. And just to illustrate, here are 18 different ways to design, conceptual ways to design a beyond lithium-ion battery versus the one way that we have for lithium-ion. So, and if you look at the materials, there may be 30 materials under consideration. versus 5 to 10 for lithium ion. So the conclusion, I've listed 3 concepts there, but there are 50 to 100 batteries in this space that you could make. And when you deal with a space like that, if you're Thomas Edison, you're probably in trouble. You can't say, I'm going to make the first one. If that fails, I'll try the second one. If that fails, I'll try the third one. You need to look at the whole space. You want to trash the 80% that probably won't work and concentrate on the 20% that at least have a much better chance to work. So this is what J. Caesar does. It looks exclusively at this big blue space, not at all at the lithium ion space, trying to lower the risk of entering this R&D space, the risk for manufacturing, and attract more players to it. It's a very tiny amount of the community right now. The more players we have in this big blue space, the faster development will go. So this is the comparison. A minute, or less than a minute really, on the prototype we want to make. 8 months after we were launched, we had a review. One of our reviewers said, oh, you're going to make a prototype. You'll put it under the hood of a Chevy Volt, you'll drive it around for a few months and see if it works, and if it does, you'll send it into production. Well, no. That's much more than we could ever do. We're going to make a prototype that I can hold in my hand. It might be messy like this with wires hanging off of it. It might be a little more polished like the example above that, packaged better. We will hand it off to a manufacturer who will make a prototype like that. Happens to be that is the battery from the Chevy Volt, and who probably will make a prototype a factor of 10 bigger than our research prototype to see how it works, and the product would be a factor of 10 bigger than that. So you're talking about probably a factor of 100 to get to the product stage. So this is our target. This is what we would like to do. So I think that's it, I'm done. This is the same slide I showed you earlier about J. Caesar. These are the takeaway messages for it, and I'd be happy to answer questions or have some more discussion. Yeah.
5 years, we talked a little bit separately about maybe another 5.
Yes.
So that's stage 4. How long from stage 4 to stage 5?
That could be 5 to, yes, let's go back to that. So it could be 5 to 10 years for that to happen. So
after stage
after
4.
this is complete. So if you look at, again, lithium ion is our guide. So 71 to 91, that was 20 years. It was really about 1985 that the present version of a lithium ion battery started to be developed. And that took 6 years. It was a crash program. So something between 5 and 10 years once you focus on the concept.
Can you talk a little bit about what role new materials like graphene or some of the aero cryogels may be playing? Most of that I think applies to supercapacitors, but how might we use this battery technology in the future?
So, great question. So a lot of come back to this this view graph. Too much animation here, this one. Oops. Most of this is due to new materials going into a lithium ion battery. They started here with a carbon anode, not a graphite anode. It quickly went to graphite. Well, it kind of accounted for that. This was a cobalt oxide cathode. We now have lots of 3 or 4 other cathodes that boost the performance even further. Those are incremental. When you talk about going to the next level, you have a lithium anode, so the feeling is that we will solve the lithium anode problem and make it operational. That'll give a big boost in performance. And we'll have a different cathode. So lithium sulfur is one of the things we're working on in the community as well. It's a chemical reaction between lithium and sulfur, which produces covalent chemical bonds. You can store a lot more energy in those bonds than you can in intercalation cathodes. So it's critical to go to the next level, to have new materials and to solve the problems just as we did with lithium ion. It's critical to have incrementally new materials, mostly alloying and playing with the ones you have to make this linear thing, linear line continue. So you need both.
So those you don't see applying to the blue space as much?
No, we do.
Okay.
So in the blue space, way too much animation here. So the blue space will have lithium sulfur. It'll have, instead of lithium, which has one charge, it'll have magnesium that has two charges. You'll have twice the energy transfer for every ion that goes back and forth. You'll have flow batteries that can be made out of cheap, abundant, organic materials that you then tune by hanging, complexes off of a carbon ring. You can really tune the solubility, you can tune the voltage, you can tune the activity level, and so on. So for that big blue space, in a sense, it's all new materials as well as new concepts. Yeah.
I just want to hear about the research process to find out those like beyond lithium battery, like blue areas. Do you have like a theory or something as a guideline to think about, oh, maybe this is possible or this is not possible? Or almost everything in this area is almost like black box. So you have to basically try out medium things in the experimental lab. Either one is more like consistent with your
That's a great question. Some of the things in this space, like lithium sulfur, were known before J. Caesar came along, but the problems had not been solved. So, and we are working very hard on lithium sulfur. We think that has a lot of potential. Some of the things in this space have not been thought of before. So magnesium sulfide is an example of that. So instead of lithium, it's magnesium, two charges. Instead of some intercalation, it's a chemical reaction with sulfur. That's virtually unexplored. So this is one of the mostly unknown things. It's not hard to write on the back of an envelope what might work and what won't work. You can do that in a few hours. You don't even need a computer. But the reason the very good ideas don't work is not because they're flawed. It's because there's a side reaction somewhere that has nothing to do with storing and releasing energy that just interrupts the process. So the active material may be consumed in a side reaction that you didn't anticipate, drops out of the picture, and pretty soon your battery doesn't work. And this is the most common thing. So when you're in this big blue space, the idea has to be good, but all the, side reactions, you have to slog through them one by one. And lithium anode, pure lithium metal anode is a good example. 40 years we have not solved that problem, even though everyone agrees that's the holy grail. We'd love to have that. I actually have some confidence that we can do that. And that's one of the, I think, best reasons to have J. Caesar, to open that space a little bit more. We will not be able to fill the whole space. We won't be able to check everything out. We just won't. But yeah.
Can you talk about how much of the stuff in the blue is stuff that would be equally valuable to consumer electronics?
Oh, all of it would be. So if I could get a 5-day charge on my cell phone, I'll pay a couple of $100 for that. I definitely.
So is that sort of true? Like, when you broke down like the stuff we want for the transportation storage and stuff we want for grid storage, it looked like there were different products.
Yep.
In a large sense. How much of the things that are in the transportation products or in the grid storage products are things that the industry that already supplies batteries to consumer electronics should be working on in some sense?
So the personal electronics folks really put all their faith in lithium ion and extrapolating that linear curve. They'd like to get the 5% per year improvement. People say it takes about a 15% improvement in battery life, battery energy density, for the consumer to notice it. But as those improvements come, manufacturers will hang a lot more apps on your cell phone. So it'll be able to do a lot more for you than it does now. But I believe, for example, a lithium anode, if we succeed in making that work, it can be put into an ordinary lithium-ion battery instantly, get maybe 20% more, 25% more battery life out of it. So I think that would happen. It's not our focus. I mean, there's a whole, $15 billion industry that's going to do that anyway. And as soon as we discover it, if we do, they'll just pick it up. And I think more power to them. There's a question over here.
To follow up this gentleman's question, are you thinking critically about the way your discovery path? So, you mentioned you use the word virtual. I mean, is there an idea of virtual material research with that you could task a supercomputer with parameters to say,
absolutely.
Wait, look at all this. We know what the chemical reaction is going to be. I don't want this side effect to happen, and give me all the good answers.
Yeah. So we use computers in two ways. We simulate materials, the so-called Materials Genome Initiative, which is All the funding agencies in the United States really have invested in heavily for the last 5 years. We're doing that. So we've looked at 1,800 cathode materials that might work with a magnesium working ion instead of lithium. And we've selected maybe 8 that look promising, and the others we're not going to mess with. So we feel that this accelerates progress. We don't have to make all that other stuff in the lab. For liquid organic electrolytes, we've now simulated 16,000 molecules, organic molecules that could be used for electrolytes. We're probably going to make 15 or 20 of those in the lab to see how well they work. These things really shorten the discovery process, and they streamline it. Use computers in another way. So once we have identified 3 components, so every battery has an anode, a cathode, and an electrolyte. Let's say we've identified those, perhaps from the materials genome work. We simulate what a battery made of those would do. So how well would it perform? Would it meet our factor of 5, at least in principle, with higher performance? And what would it cost to make it? Could we make it for a factor of 5 less? And this thing is called techno-economic modeling. Crazy term that is totally logical. But so we look at all the battery systems we could make, and if they don't meet our criteria, we don't make them. So again, we're selecting only the ones that have a good chance of success. And these are things that are not done typically in battery R&D. So we're bringing this to the table, and let's see how it works. It's an experiment, but we have a lot of confidence in it.
If you go to your slide with the prototype, the timeline for the prototype, we've got how many years from breakthrough to prototype? Well, just say at the low end we're talking about 5 years, because the goal of things being we're going to do these things in the next 5 years, or maybe we re-up and get another 5 years. It sort of seems all conditional on the breakthrough having had happened. To say we're going to do it in the next 5 years means that we've already had the scientific breakthrough, and we've got this thing that we've already did, and now we're going to get it through. As opposed to, we've been 5 years away for the last 20 because we haven't had that first step.
Yeah, you're right. So some of those breakthroughs have happened. Lithium sulfur, we know how the reaction works, and we've done a lot of computation on lithium sulfur side reactions too, because that's what usually kills you. So some of those things have already happened, and it's a question of slogging through the side reactions that are preventing them from actually going into practice. So it's not the breakthrough itself. It's all the interfering, subsidiary things that you have to solve. The other point is that the only guide we have is lithium ion. It was 20 years from at least thinking that we could do it this way to actually doing it. It was probably 6 years from 1985 to 91, where we actually knew what we were going to do and we had to make it work. So that's a guide here. But it's like your investment. Past performance is no guarantee of future returns. So maybe that's a good guide. Maybe we can do better. So in J. Caesar, we're interacting across the whole chain from discovery to prototyping. It might go faster. That's our hope. We don't know yet. We'll have to see if it does. Yeah.
On the slide with the lithium-ion battery, it shows, like with most technologies, the cost decline dramatically over time. If you're choosing your materials ex ante to say we need to meet a certain cost criteria, then you're restricting, in a way, you're restricting yourself. You're restricting away from this not natural process, but something that would be happening anyway of cost declines.
Indeed.
And are there a lot of So you choose cheaper materials, but then there may be very efficient materials you're not choosing, and you could assume that the economics will take care of the production costs later.
Boy, that's a great question. So ionic liquids are a perfect example of that. Almost everyone agrees that that would be a much better electrolyte than the organics that we're now using. They're really expensive. And so actually nobody has tried too hard to make ionic liquids the electrolyte for batteries. That cost curve could happen for ionic liquids. And we do in our techno-economic modeling, we make an assumption about production and that learning curves, that lowering the cost. And so our predictions are at the end of that learning curve. So after here, 10 years or so of production, what would it be? But you really don't know what's going on there. So I think there's as much intellectual and intuitive judgment as there are models that you use. But it's a judgment call. So, yes.
So one thing I'm always fascinated by in general is where's the proper role for government-funded research? Where does that run and where does it end, and the private sector take over? So it's almost impossible to answer with a quantitative precision that I think a lot of us are especially comfortable with, but just qualitatively, what you guys have done in the last, this is 2.5 years in, right? What would have been done by the private sector? Any of it?
Oh, much less. Because the private sector hates risk. So with a lithium-ion battery, if I can improve the cathode a little bit incrementally and get a 5% better performance, I've won. There's a lot of return I'll get for that. With a beyond lithium-ion battery, I have to find 3 materials, a cathode, an anode, an electrolyte, all of which perform 5 times better or much better than lithium-ion, and they have to work as a system. And that's really beyond everyone. GM and Toyota can think about that. Most institutions can't. So they just don't do it. And I think that it's the nice thing about J. Caesar, we have an opportunity, government funded, to assume that risk. We don't have to make money. So if we can get that risk down, we could really do a service for the community. We'll see if we do. But I think a lot of that would not have happened.
And so where did you hire folks from? I mean, this is like a space that I guess they couldn't have been hiding in the private sector because they had skills that were.
Yeah, I believe that in the private.
Were they buried in universities like the rest of us, or?
Yeah. So we have 5 universities, we have 5 national labs, we have 4 private sector companies. The private sector companies, actually, most of them are not participating in the bench level research. They're kind of watching what we're doing, and we talk to them. Universities and national labs are. And we were lucky enough to get I would say, a very talented group of people to do that. So they're versatile. When they see something's not working, they switch to something else, and they don't, it's not the end of the world for them. But I think in the private sector, people are distracted by the short time horizon, the need to make money in 6 months, and they just don't do this. So in that sense, it's a new thing.
And one last question, I'm sorry I'm hogging the mic.
Oh, go.
Here. And who owns the IP at the end here? How does that work?
Great question. So we started working on our proposal 2 years before we turned it in. And that was probably 1.5 years before they even issued the call for the proposal. And because of that, we had built up a lot of trust among the players. So we were able to execute an IP agreement before we even put the proposal in as to how we would treat that. Basic features are, like anywhere, whoever invents it owns it. None of our partners can...
Scientists own it?
Pardon?
Is the scientist invent it?
Sure, yeah.
From government-funded research?
Well, there's a stake. It's actually not much, but they do get something, typically. But one of the main features, I think, which made it work, is that none of our partners could expect an exclusive agreement. So even if they were the main partner inventing it, they agreed, okay, well, we won't take it as an exclusive, license. We could do that. We have to negotiate. So maybe that would be the right thing to do in some cases, and if so, we can do it. But nobody can expect that. We have one negotiator. It happens to be Argonne by agreement. So whoever wants to license doesn't have to go to 14 different partners and make 14 agreements, make one. And we pool a lot of, at least the national lab IP that already exists is pooled with the stuff we're inventing. So that makes what we've invented, what we invent or will invent, more valuable because it has a lot of IP stuff with it. So we haven't actually encountered a case where we've had to license yet. So let's see what happens when, but our hope is that we've streamlined that process also.
So one hears a lot generally about the valley of death. I'm wondering, is that sort of why you think that these 4 non-participating commercial partners will come in? Where would that come into this? Or is there just such demand through consumer electronics or need for the grid that this would get adapted and adopted anyway?
So great, I didn't mention it. We have also 90, I think, affiliates which are folks that might want to receive our technology, or maybe they're university research groups and so interested in what we're doing. We talk to our affiliates at least once a year, actually more like 2 or 3 times a year. We talk to our private sector partners. One of them is JCI, biggest manufacturer of lead acid batteries. And we hope to address the valley of death by not doing things that can never pass the valley of death. So in a sense, it's as much what you don't do as what you do. By talking to JCI and our affiliates, we get an idea of what is needed. And we are a very outcome-driven organization. So we have a strategy that we reevaluate every 6 months at least and ask, is it still the best strategy? If we see that there's a disconnect somewhere, it will never work. We de-emphasize that, or sometimes even drop it. But we do it by talking. So we hope we're doing it better. I think you have to go by what actually happens. We haven't gotten to that point yet.
What new developments in this space are you most excited about?
Wow.
And if you're going to predict where the next breakthrough might come from, if it weren't JC's, or where would that be and why?
So I think the biggest opportunity is in what's called flow batteries. I didn't really talk about them. Tanks of liquid instead of solid electrodes. They're liquid with dissolved electrodes, either at the molecular or the suspension level, nanoparticle level. That's not very well explored. And our idea of using organics for that opens up a whole new range of things that might work. In the last year, we've actually made 2 very important discoveries, you might say, or we've adopted approaches using polymers instead of electrodes, instead of molecules, and cross-linking those polymers into colloidal particles, which are quite big. They might be 3/4 of a micron in size, as the active particles. Neither one of these things was ever out in the community before. So now we can, depending on what we hang on the polymer backbone, we can design the battery to operate in certain ways. So we're 1 year into that direction. I actually think it has a lot of potential. I have no idea what the outcome will be. I think lithium sulfur has a lot of potential. If you could do it, everybody can write down all the batteries they would make. There's some problems with, they're all side reactions that we need to solve. We actually have 3 ideas that we're following to solve those problems. If they work, that would be great. I think there's a high potential there. I have the least, don't quote me on this, the least confidence in using magnesium or a multivalent battery, just because there's a lot of problems there. Nevertheless, we're trying.
Does your organization have the capacity to pursue multiple avenues all the way to the stage 4? It occurs to me that there will be some batteries which work only at scale. Some of the liquid metal ones come to mind, and ones that are too expensive to work except small. So how could you come up with 4?
Yeah, in fact, we have 4 ideas right now that we're following.
You might take them all the way if you can defeat the blocks.
Yeah, our intention is to take them all the way. Why? Because we know that a lot of them will fail. The history of lithium-ion tells you almost every good idea you have doesn't work. And if you can solve all the side reactions and all the interfering, things that have nothing to do with storing or releasing energy, it will work. That's what happened with lithium-ion. So lithium-ion, there's basically one battery only that came out of that whole operation. It's the one we use now. In the beyond lithium-ion space, it's big enough that there's more than one solution, we feel. And so we want to follow 4. We have 5 years, sort of 2 years left in our first 5 years, and if we're lucky enough to get renewed, we get another 5. We want to follow the 4 until we find why they won't work, and then we'll more or less quickly drop them and go after the ones that will work. But we do want to follow in parallel all 4. This is also unusual. Most R&D organizations won't do. The startup would never do that. Startup says, I think this is going to work, I'm going to put all my eggs in that basket, I'll make it work or I'll fail. We say, well, we have a range of things that may work, and as they fail, we'll drop them off the side and put our efforts on the ones that look more promising. It's really different. But we do want to carry all of them all the way to the end.
Are you guys seeing or shooting for big progress on things besides cost and energy and power density? So I'm thinking of like cycles.
Oh, yeah.
What are you seeing? I guess, is there anything exciting on cycles?
So lithium-ion battery, just because of the way it's made, you can't charge it very fast. And it will wear out, from your computer. It's going to wear out eventually. And how many cycles is it? Well, you'd like to have more. Depends a lot on how you use it. If you only charge it to 80% of full and you start charging when it gets down to 40%, you'll get a lot more life than if you go from 0 to 100 every time. So it depends on how you use it. Flow batteries, why do they fail? Because as the lithium ions go into the cathode or the anode, their volume changes, there are changes in those crystalline materials, they degrade, they crack, various things happen. In a flow battery, those crystalline materials are replaced with liquids. And there basically is no degradation as you cycle. The liquid is the liquid always. So they have a much longer life than a crystalline battery would have. And people are saying, you could get 20 years of life out of it in a good battery like that. So there's a variation there, but we do look at everything. So we've plotted the energy density. That seems to be one of the most important things. The charging time is really important. The lifetime is really important. A factor of 2 in life means a factor of 2 less cost. Right. So, yes.
How are you accounting for the sustainability or resource intensity of your starting materials when you're looking at the new sources of anodes or cathodes or whatever?
So go back 15 years maybe. I don't think in the R&D world many people looked at sustainability from the very beginning. It started maybe 7 or 8 years ago with solar cells. That's when I remember papers being published saying, well, here's all the ways you could make a solar cell and here's the materials you could use. Only a few of them are abundant enough to make a big difference if these things are widely deployed. So we think about that all the time, in fact. Lithium, probably there's enough in the world that if every car were an electric car and used a lithium-ion battery, we wouldn't run out. You'd have to recycle. And so you think about recycling and you think about abundance and you think about cost. The most expensive thing in a lithium-ion battery is actually not the lithium, it's the cobalt. So can you get rid of that cobalt? And lots of people are working on that. But we do think at the beginning. So we don't want to start in a discovery process, discover something that could never be scaled up. So that's fundamental to our thinking. But that's different. 10 years ago, we would have thought differently.
Okay, I think we have time for one more question.
Here's a guy.
If I build a thermal plant today, running on coal and natural gas, it's got a 50-year lifespan. Where do you see this going insofar as in 50 years, are we going to be off that centralized plant model? We're never going to have to build centralized plants. We're going to have PVs that are 40% efficient. We're going to have battery storage.
Yeah, great question. I don't know. The only thing that you know about predictions is that they're wrong. So I hate to predict, but I doubt that we would ever get off centralized plants. So we're going to need some of them, New York City and Chicago and big cities. They're going to need that. We will have much more distributed generation, way more than we have now. That probably, if you want to do it right, you probably want to have microgrids that interact with each other, and that's an architecture we don't have now. So the grid is just not designed that way. It's going to take a long time to just, even if we decided right now that's what we want to do, it might be 50 years before you achieve something that is approximately what the level and the deployment of microgrids that you might envision. So I think it's a slow process. And it's going to take a long time for that to happen. We'll learn in a way that's good. We'll learn as we go and make enough mistakes that are not catastrophic and change our vision. So
please join me in thanking George.